have questions, type them in the chat. If you would rather not type them in the chat and you want to send me a remind message, you can as well. But this is going to be some new stuff that we're getting into today, which is why I have my whiteboards behind me too, just to try to go through problems that way. So like I said, I have the do now presented up on the screen. And so for number 1, it says, why does a higher temperature cause a reaction to go faster? So the video that you guys watched in class yesterday was on kinetics, the intro to kinetics, which is simply looking at rates of reactions. So how do we make a reaction go faster? How do we make a reaction go slower? So this first question wants to know specifically why a higher temperature causes a reaction to go faster. Now we're going to be tying things back to collisions like we did with gases. So if you think back to when we talked about gases and we looked at temperature of gases, remember that changed the average kinetic energy of the molecules. So when we change the temperature, it's still going to be the same thing. We're changing the average kinetic energy. So not only are we increasing the speed of the collision, so how many collisions are happening, we're also increasing the energy of the collisions. So temperature will affect the energy of the collisions. That's the only thing that will affect the energy of the collisions. So for number 1, why does a higher temperature cause the reaction to go faster? That is because of C. There are more frequent collisions and they are of greater energy. So on your do now sheet or your do now paper, under Thursday for number 1, you can put C. Number 2, why does a higher reactant concentration make a reaction faster? So when you think about concentration, you're thinking about moles per liter. When we talk about concentration, we're talking about molarity. So a higher concentration means a higher number of moles per volume. And so if we have more moles, we have more reactant, then we have more collisions. Remember that the only thing that will change the energy of the collisions is temperature. So if all we're changing is concentration, then we are allowing more collisions per second. So number 2 is A. So number 1 is C, number 2 is A. Right? So that's actually all for the do now today, just 2 multiple choice questions. Again, just in case you missed it, number 1 is C, number 2 is A. So what we're going to do is we're going to start, and I'm just going to click through instead of presenting. Oh, I should present the screen. I'll just bring this forward so that we can see it. So for I guess the rest of this week, so today and tomorrow, we are going to work through kinetics. So I have the lesson plans up here. I noticed that people were going in and out of the lesson plans yesterday, but we are going to start kinetics, and we're only going to get through the first 2 videos before break. So we're going to focus on the first 2 videos today and then into tomorrow. We will have the first kinetics quiz before break. So that will be Monday, and I know it sounds so soon, but we will do lots and lots of practice. I will make sure that you feel good about this before you take the quiz. And I know everyone is going to be virtual, so we will make sure on Monday, right? Next week we're virtual. And so I'll make sure that questions get answered, right? So don't think that it's like, oh, here we go. We will go through lots of examples. I will make sure to answer your questions, and it is multiple choice. So it will be 20 multiple choice questions covering just the first 2 videos. I'll have you watch the second video tonight, and then we'll go through more examples tomorrow. Mastering is open. I was looking yesterday at Mastering, and I noticed that there are people that already have the first 7 questions done. So Mastering is open. The due date is not until after break. So it's, I believe, the week or week and a half after we get back from break. So please don't try to do it all right now. Kinetics is completely new. Don't try to work through it all. Just do it little by little. You're going to notice in the lesson plans that I have it broken up. I have it chunked just to help as well. I did also want to put the picture of what you see on Mastering up here. So if you notice, I actually just took this screenshot from Mastering yesterday. I have it broken down by video again. I have the pages to the e-text linked in here. And then I also have the pages in the class textbook. So I don't have one of the old books here. It's in my classroom. But the silver, like gray book, I also just put a PDF of that on Google Classroom. So I have a PDF of our current textbook that we use. So if you have a hard copy of the textbook, that's what I mean by class textbook. These pages that are linked is the newer edition that's in mastering. And so I have both sets of pages, whether you want to use the old book, which is the PDF or the hard copy, or you want to use the e-text. You will notice in here as well that there are tutorials built in because this is completely new. And so this is your view as soon as you click on the assignment. I put extra credit or practice. So just make sure that you're paying attention to whether it's extra credit or practice. If you just click through the assignment, some of them are practice, and it doesn't necessarily tell you as you're working through mastering. I also try to give some other tips as well. So after today, you can go through number 7. And then after tomorrow's video, you'll be able to work through 8 through 19. So that's a good chunk of it already. If I remember, it's 38 points with 7 extra credit points built in. So you could get up to what is that, even 45 out of 38. So there's lots of extra credit built in. Again, kinetics is brand new. So please make sure as we're going through anything today, tomorrow, next week, that you're asking questions. Don't be afraid to type them in the chat. Send me remind messages. If you prefer not to type them in the chat, send me emails, right? Just make sure that you ask as many questions as you can. Hopefully we get through kinetics, at least seeing each other a little bit in person, but if not, that's fine. Kinetics is one of my favorite things to teach. I don't know why. I love teaching kinetics. So hopefully I'm able to answer all of your questions. Again, if not, if you need me to try to find a different way to explain it, I'm more than happy to do that as well. So we're going to start by just briefly going over some questions that people had. I usually do a demo with glow sticks, but since I'm at home, I keep a lot of random things at my house, and glow sticks are not one of them. So I went through and I just found pictures of essentially what I do in class. So in class, what I do is I have 2 glow sticks. I have people crack them open so you can tell that I didn't do anything to them. And I put 1 glow stick in cold water and 1 glow stick in boiling water. And what we see is that one is clearly burning brighter than the other. And that represents the rate of a reaction. So the brighter one is reacting faster because it's in hot water. The dimmer one is not reacting as fast because it's in cold water. So there are different factors that will affect the rate of a reaction. So another word for rate of reaction is speed. So the rate of reaction is how fast a reaction occurs. Now these that are listed, these factors are on page 1 of your notes. So you can go through and look at everything that's right on page 1. I just kind of paraphrased it right here because there were some questions. So the physical state of the reactants will affect the rate. So homogeneous mixtures tend to react faster than heterogeneous mixtures. As we think about what affects the rate, the reaction rate is always based on the number of collisions between reactant particles, because a reaction has to be between the reactants. So anything that increases the collisions between reactants will increase the rate. So physical state kind of ties into surface area. There were some questions on homogeneous versus heterogeneous mixtures. We don't see that as much as we do powder versus a pellet. So think about like a sugar cube versus like powdered sugar. So the powdered sugar has more surface area, has more contact area, so that will react faster. Concentration. So again, moles per liter. When we talk about concentration, it's always molarity. That will affect the rate, temperature, and then presence of a catalyst. So right now, all we have to know is that a catalyst speeds up a reaction. We have a whole nother video specifically on catalysts and how they work and why they work. But for now, we just have to know that a catalyst speeds up a reaction. So as we're looking at, and we're going to do some stuff on the next slide, I'm going to actually have you guys try some examples. We're going to use Pear Deck again, like we did. But as we go through this next set of examples, and it's actually what's at the bottom of page 1, where it says explain why the reaction rate is different. You always want to tie it back to collisions between reactant particles. If there are more collisions, there's a faster rate. If there are less collisions, there's a slower rate. And it has to be between reactants, because in a reaction, your reactants go to products. So you always want to think about that as well. So what we're going to do is we're going to look at how reaction rate can be affected. So I'm going to switch over to the Pear Deck slides, and we have done Pear Deck. We did it one other time when we were remote, and so I'm going to share that tab with you. And as we go through this, remember that I can see who's typing, no one else can. So I want you to try to answer the question the best that you can. And what we're going to do, so again, we're on page 1 of the notes. So if you have your notes out in front of you, we're going to be doing those 5 examples at the bottom of page 1. And so what you can do is you can go ahead and you can open a new tab. And you can go to joinpd.com and you can type in this code, or I'll go ahead and I'll put the link in the chat for you as well. So you can always just click on that link instead. So for this, again, we're going to be going through just the 5 problems, the 5 examples at the bottom of page 1, and we're going to go one by one. So you're not going to type all 5 in at once. We're going to go one by one, and we're going to talk about each one. The reason that we're going through these is because these are the types of multiple choice questions that we see with kinetics. Right? Explain why, and then it gives you these answer choices. So we're going to really talk about the why with these. So again, you can either go to joinpd.com and you can type in this code, or you can click on the link that I put into the chat. And once I go ahead and I start it, if for some reason it kicks you out or something like that, you can always join back in. Okay, so again, what we're going to do is we're going to look at how reaction rates can be affected. So let me go ahead and I'm going to share this tab instead. And again, we're just going to go through one by one. So what I want you to do is I want you to just focus on number 1. So explain why the reaction rate is different if we have 10 grams of powdered zinc versus 10 grams of a strip of zinc. So why would 10 grams of powdered zinc react with HCl more quickly than a solid strip of zinc that weighs 10 grams? I went one too fast. So powdered zinc has a greater surface area. So here's what I want you to think about when you think about surface area. Surface area is contact area, right? Contact area. How much contact is it able to come, collide with? So powdered zinc, the entire side of each small piece of powder can come into contact with HCl. The strip of zinc, only the outside can come into contact. So powdered zinc has a greater surface area. Greater surface area means more collisions between reactant particles. Notice how we tie it in to reactant particles. So it always ties in. Oh, you can't type in. Okay. So we'll go through these. I know there's going to be one that you can go in. Let's check. So we'll go through these and then we'll have some questions. I'm not sure why it's not letting us type. So for the second one, so what we can do is we can at least write in our notes for now. So at the bottom of page 1, we'll just write these in, and then we'll make sure that at least the multiple choice questions work at the end. So for number 2, a sample of magnesium metal will react more quickly in 10 molar HCl than it will in 1 molar HCl. So here's what I want you to do when you're looking at questions like this. Look at what is different. What is different between the two scenarios? So if we're looking at what is different between the two scenarios, right, we should see that the concentration is different. 10 molar versus 1 molar. And so think about, okay, so if we have 10 molar, it's a higher concentration. So when we're thinking about this, a higher concentration of acid means there are more collisions between reactant particles and a faster rate. So again, tie it back to collisions. So at the bottom of page 1, we can write these into our notes. So bottom of page 1, right, we're adding these in to each one. So notice everything is tying it into number of collisions. So for number 3, an Alka-Seltzer tablet will dissolve more quickly in water at 80 degrees than in water at 20 degrees Celsius. So you could try this at home. If you have Alka-Seltzer at home, heat up some water and verify that this is happening. So again, look at what is different. Temperature is different. Temperature increases the energy and the speed of the reactants. Faster means more collisions with greater energy. So a higher temperature means a higher average kinetic energy. Your reactant particles will move at a faster speed, so there are more collisions between reactant particles and a faster rate. So again, notice how at the beginning of each one of these, we're talking about what is different in the scenarios and how it affects the collisions, because collisions is what's going to change the reaction rate. So then, oh, I just put the answer up before. Oh, well. So describe the role of a catalyst. All we know right now is that a catalyst speeds up a reaction. The most important thing about a catalyst is that it speeds up the reaction without being used up itself. So that's really important, is that a catalyst speeds up a reaction, but it's not used. So it's there before and it's there after. And we'll, again, after break, we'll look at exactly how catalysts work. So we'll look at what the point of the catalyst is. How does it actually speed up the reaction? So then finally, number 5, as the frequency of collisions between reactant molecules increases, how will the rate of reaction be affected? So as the frequency of collisions between reactant molecules increases, how will the rate of reaction be affected? So as the frequency increases, that means we have more collisions, right? And more collisions will result in a faster rate. So as the frequency of collisions increases, the reaction rate will also increase. I think I know why this also isn't working. And I think, so make sure you have these. So while I'm flipping back over, I'm pretty sure it's in a different Google Slides. While I'm flipping back over, make sure you have this written on page 1, right? So we'll take a break right now. Make sure you have this written at the bottom of page 1. And then we'll go ahead and go to the next set of questions in 1 second. That way you can actually type and you can actually answer the questions. So let me open this. And again, these first 5 were at the bottom of page 1. So these aren't technically any of the examples. And the next thing that we're going to look at is also not part of the examples, but rather they're practice AP questions. And so here's what we're going to do. In order for you to type and answer questions, we have to go into a different slide deck. So I'm going to end this, right? And I know that you couldn't type in this one because this is the practice slides that I posted on the website. And I actually made a separate one with all of these questions in a different Google slide deck. So this is what I get for making multiple slide decks. And so what we'll do, I just ended it, and it's still kind of loading and thinking. All of these actually, like this is everything for today. So these are all the examples that aren't in Pear Deck and everything as well. These are all already on the class website, and they're also tied into the Do Now slides. So the Do Now slides are very long, but that's because I'm putting everything in there. I know a lot of people will access Do Now slides as well. So here's what we're going to try to do. We're going to share this tab instead. And it's going to click you through the ones that we already went through. So once we join this, it's going to be all the ones we already have seen. But I'll fast forward. I'll click through. So if you're in the other Pear Deck one, I ended it. So because there were no Pear Deck questions, right? It was just like I was clicking through the Google slides. So here's one that I promise you're going to be able to answer questions in. And so I'll share this link with you. So let me share this link with you. Put it in the chat. There you go. So now we're going to be able to click through. Make sure next time we do one of these that we're using the right slide deck. But thank you for letting me know that you couldn't type. There we go. So now we'll be able to go through and we'll be able to click through everything. So now I'm gonna click through these. So I know stuff's gonna pop up. We're gonna skip over it because we've done these, right? So here's where we were gonna type. Now here's what I want to look at next. So see, now you can answer the questions. So here's what we're gonna think of. And these are actual multiple choice questions or free response questions I turned into multiple choice questions. So we have this equation at the top, calcium carbonate plus 2H plus yields Ca2 plus H2O plus CO2. And then we have two sets of data. So we have experiment 1 and experiment 2. Notice it gives us mass, volume, initial concentration, and initial temperatures. So which experiment, if any, will have the faster initial rate of formation of CO2 and why? So again, we want to look and we want to see what is similar, but what is different. Because what is different is more than likely going to be what affects the rate of reaction. So if we look at this, right, look and see what's different and which one will affect the rate of reaction, right? Which one will cause it to have a faster rate of reaction? Good, I see. So far we have 15 people that have answered, and 17, everyone has answered the same thing. So if we take a look, all right, notice. And again, this is not in the notes anywhere, but these are practice AP questions. I actually pulled these questions directly from practice kinetics test. All right, good. So experiment 2 will be faster because it has a higher concentration. So if we want to be even more specific, right, we can say that experiment 2 will have a faster rate of formation because it has a higher concentration resulting in more collisions. More collisions is the important part there. All right, so if we look at the next slide, now we have experiments 3 and 4. So we have calcium carbonate. It's both 5 grams. One is powder, one is pellets. So pellets is a common word that we use in AP Chem And it's like small discs. So it's almost like a small disc of solid versus powder. So you have to crush up pellets to get to powder. Same volume, same concentration, same temperature. So which one will have the faster initial rate of formation? Good. So we have 13, 14. Good. So it's going up. So again, when we talk about surface area, I want you to think of it like contact area. The more that the reactants can come into contact with one another, the faster it will react. So most people chose experiment 1, which is correct. So experiment 1 will be faster because of the difference in surface area. So powder, right? Again, you could try this at home if you had like sugar cubes, or even if like sugar gets clumped together, it's going to react faster as a powder, right, or as small crystals than as a big chunk. So if you've seen the big salt block on my desk at school, if I tried to throw that salt block out here into the snow, it's going to take a while to dissolve versus the salt that I can lay on my driveway, right? That's small crystals that will dissolve faster. Good. So here's just a picture to show you. This was part of a multiple choice question. So this shows you what a pellet would look like versus figure 2, which shows what a powder would look like. So notice how the pellet, only the outside of the pellet can come into contact with the other reactants versus the powder, where you have all sides of each individual small piece of powder that can come into contact. So the powder, figure 2, can come into contact more than figure 1, which is the pellet. And so more contact area means more collisions, faster rate. So then the last question, so experiments 5 and 6, which experiment will have the faster initial rate of formation of CO2 and why? So again, look at what's different. And then I want you to think to yourself again, tie it into collisions. Why will it have a faster rate of formation? Always tie it back to collisions. Just like with gases, kinetics is going to tie into collisions a lot. Good. So we have 15 people that have answered. 19. So if we take a look, so it was between E and F. So experiment 2, if we look back, experiment 2 has the higher temperature. The higher the temperature, the more collisions and the faster the rate. So I guess not experiment. I just did 1 and 2 for all of these, but yeah, the second one. So experiment 6 has a higher temperature, more collisions, faster rate. Good. So again, this is just looking at factors that affect the rate of reaction. And so we have surface area, we have concentration, we have temperature, and then catalyst. Those are the ones that we see the most. I put the physical state of reactants on our notes, but we don't really see that as much as the other 3, just like what we looked at on here. So good. So that worked a lot better, right? Now that I was actually on the right slide deck. And so again, this last part was not within the notes, but they are in the do now slides and in the 5.1 practice slides if you want to look at those instead. So before we go on to the examples that are actually in our notes, are there any questions on factors that affect the rate? Anything on? There was another question on volume. So when does volume affect the rate of reaction? And volume only affects the rate of reaction if you're looking at gases. Because volume, if you change the volume, you're changing the number of collisions of gas molecules. So if you're looking at a rate of reaction between 2 gas molecules, or 2 or more gas molecules, then volume will affect it. If you're looking at solids, liquids, aqueous solutions, volume will not play a role. So if we would have changed the volume in any of those reactions, any of those experiments on the last few slides, that would not have affected the rate of reaction because they were solutions. If it's gases, then volume will affect it. Okay, so what we're going to do here is we're going to go through some examples. Now, these are the examples that are in your notes. So example 1 actually is on, and I have my notes packet out here as well. Example 1 is on page 3. Now, to do some of these examples, it's going to be easier if I can write things out. And so I'm presenting my screen so that you can see the examples. But if you also notice behind me in my video, I have my whiteboard. So I would recommend, like as I'm going through something on a whiteboard, if you hover over my video, you can pin me to the screen and that's going to make it really big. And then when I'm talking about the slides, I'll say, if we look at the slides, and then you can like unpin and look at the slides. I have essentially written out examples 1, 2, 3, 4, and 5 on these whiteboards. But obviously I didn't write all of the information because I only have 2 whiteboards. So, and I'm going to use different colors. If it's hard for you to see on here, just let me know. I'm going to pin myself to the screen so that I can see it as well. And so what we're going to do is we're going to look at example 1. Again, example 1 is on page 3. And these first 4 examples are looking at that rate of appearance and rate of disappearance. And rate of appearance and rate of disappearance is all about the stoichiometry. So it's all about looking at the stoich. Now, at the end of the video, you looked at something that was like 1 over A times the rate of A. I'm going to show you an easier way to do it. So I'm going to show you an easier way to look at rate of appearance and rate of disappearance. And I learned this from an AP teacher about 3 weeks ago. And it's so much easier. So I'm going to show it to you. So when it comes to these examples, for example 1, they don't give us any numbers. So we're just going to talk about how the rates are affected, right? And we're going to write it down conceptually. We're going to look at how the rates are affected. So if we look at example 1A, so it wants us to talk about how the rate of disappearance of each reactant is related to the appearance of each product. Now you might notice that you see negatives in front, like in the video when we did like negative 1 over A times the rate of A. That negative was to make sure that your rate that you were expressing was always positive. So the value, the numeric value for any rates will always be positive. But just remember that reactants always disappear, products always appear. So for example 1A, notice how, so if you notice how on this, right, every single one of these in A, every single coefficient is a 1, which means all of the rates are equal. So for 1A, we can say rates are equal. Rates are equal because all of the coefficients are the same. So all the rates are equal because all the coefficients are equal for 1A. For 1B, if we take a look again at the coefficients. So again, when you're looking at rate of appearance or rate of disappearance, when you see those words, appearance, disappearance, that should immediately tell you to look at the coefficients. So if we take a look at this, N2O and N2 have the same coefficient. So their rates are equal. So we could say rates of N2O and N2 are equal. Then compare those coefficients to oxygen. So they're twice as much as oxygen. So if we think about it the other way, let's focus on oxygen compared to the other ones. Rate of oxygen is half that of N2O and N2. So the rates, again, I typed it out on this slide so that you can see it a little bit more easily. So the rate of N2O and N2 are equal because the coefficients are the same. The rate of O2 is half that of N2O and N2. So the rate of O2 is half that of these other two because the coefficient is half of the other coefficients. And this is going to make a lot more sense when we can put numbers to it. Right? Once we can put numbers to it, it'll help. Especially with one like C, right? When your coefficients are not 1 to 1. So if we're looking at the rate of each one, so for example, nitrogen has a coefficient of 1 compared to the other ones. So the rate of nitrogen has a coefficient of 1 is 1/3 that of H2 and 1/2 that of NH3. Compare the coefficients. 1 is 1/3 of 3. 1 is 1/2 of 2. So here's how I typed this one out. So the rate of N2, right, is half that of NH3, 1/3 that of H2. The rate of H2, right, which is now a 3 for the coefficient, is 3 times that of N2 and 3/2 times faster than NH3. Then NH3 is 2 times faster than N2 and 2/3 faster. Or I guess 2/3 as fast as H2. So again, without plugging numbers in, it sounds like, what? But we're going to plug numbers in the next one. So this was all conceptual. And what we just did is preventing us from writing out that like negative, delta N2 over delta T. No. Instead, we just focus on the coefficients, almost like stoichiometry. Okay, so this example was much more conceptual. After we go through example 2 and example 3, hopefully that's going to help a little bit more. Again, I keep flipping back to the meat just to see if you guys have questions. So if you have any questions, just type them in the chat. Again, these are all part of the practice that's within the Do Now slides and the practice slides that is on the class website. So something to remember for example 1 is that the rate of appearance and rate of disappearance is determined by the stoichiometry. So if we take a look at example 2, so example 2 is at the top of page 4. It says when the chemical reaction above is carried out under certain conditions, the rate of disappearance of D is 2.5 times 10 to the negative second molar per second. So rate of reaction is usually given in molar per second. Sometimes we see it in moles per second. But the rate of disappearance of D is 2.5 times 10 to the negative second. What is the rate of disappearance of E and the rate of appearance of F under these same conditions? What if we want to find the entire rate of reaction? And then we'll look at part B. So I'm going to look up here on the whiteboard, right at the bottom of the whiteboard up here. I'm going to adjust this a little bit. So for example 2, I have the balanced equation written out. And that's the balanced equation that they gave us. And I said the rate of D is 2.5 times 10 to the negative second molar per second. Here's how we can do this without all of that complicated rates, coefficient like 1/2, 1/3. Here's what we're going to do. We're going to treat it like stoich. So here's my rate of D. I'm going to do the times sign fraction bar like we were doing a stoichiometry problem. Right? So this is D. So D is on top. I'm going to put D on the bottom. We want to go to E. Right? It first asks us about the rate of disappearance of E. So I'm going to put E on the top. for every 1 D, there are 3 E's. 2.5 times 10 to the negative second times 3. Calculator's missing. Well, I can do this. All right, 2.5 times 3, 7.5. So there's E. Then for F, we can do the same thing, except instead of E here, I'll do it in a different color. So instead of E on the top, we can put F on the top. Because for every 1 D, there's 2 F's. So 2.5 times 10 to the negative second times 2 is 5.0 times 10 to the negative second. So notice how easy that was. It's just like setting up stoic. It's like using a mole ratio, except we're not even using like moles. We're truly just doing 1D to 3E or 1D to 2F. Now, the idea of the rate of reaction, and I added that in. You're going to notice that you don't have the rate of reaction written in A. I just wanted to talk about it because I noticed that in one of the practice questions, they asked about the rate of reaction and not. Notice how this is the rate of D or the rate of E or the rate of F. Well, the rate of reaction, what we could do to make this the rate of reaction is that for 1D, the reaction runs 1 time. So when you have 1D, you have the reaction running 1 time. So the rate of reaction is also 2.5 times 10 to the negative second, right? The rate of the overall reaction. This will make, we'll come back, we'll like circle back to that once we actually look at rate laws and we look at rates of reaction. But it's just important to keep in mind, like if we have 3 E's, the reaction runs 1 time. 2 F's, the reaction runs 1 time. So that's just something to look at with the reaction. So now if we look at part B, why is it typical for reaction rates to decrease over time as a reaction proceeds? So think about it. Rates of reaction are based on reactants. If you have less reactants, you have less collisions, right? And less collisions means a slower rate. So if we take a look at, here I have everything worked out on this slide. So this might be a little bit easier to read than mine. So here's for E, right? Reactant E is consumed at 3 times the rate of D. It's based on the coefficients. So notice 1 reactant D for 3 E's, multiply. Product F. Now, E is disappearing and F is appearing, but notice that the rate values are still given in positive numbers. So the rates are always given in positive numbers, but then we can just say appearing or disappearing after. So F, we start with D, multiply by 2 because of the coefficients to get to F. For the overall reaction, we still keep stoic in mind. So for every 1D, the reaction runs 1 time. Again, we'll come back. We'll circle back to this overall reaction idea probably right when we get back from break. So then part B, why is it typical for rates to decrease? So this is usually what we see. Over time, rates will decrease. They'll slow down. So you might notice that a reaction is occurring a lot right away, and then it's going to slow down because the rate of reaction is based on the number of reactant molecules that are colliding. So as the reaction proceeds, the reactant molecules are being used up. They're turning into products. So if there are fewer and fewer reactant molecules, it's a slower rate. Right? So that was example 2. Any questions so far? Okay, so I'm going to move my whiteboard. Let me make sure that I don't knock anything over or that my tripod doesn't fall over. Okay. So for example 3. So example 3 says, for the reaction represented above, the initial rate of decrease in X So the rate of decrease of X is 2.8 times 10 to the negative second per mole per second. We're going to change this to moles per second. What was the initial rate of decrease in Y? All right, so the rate of X is 2.8 times 10 to the negative second moles per second. What is the initial rate of decrease in Y? Rate of increase or decrease or rate of appearance or disappearance is always based on stoic. So 2.8 times 10 to the negative second, I'm going to start with that. And that's of X. Use the balanced equation. Right? If we use the balanced equation, for every 1x, there are 2 y's. So we can do 2.8 times 10 to the negative second times 2. So again, this is instead of doing that whole thing at the very end of the video. We can just use stoic like this, and that'll give us our answer. So 2.8 times 2 is 5.6. So 5.6 times 10 to the negative second. Oh, third. Well, it's fine. For us, it'll be second. I just missed writing lots of things in this example. I missed lots of units, and so we're fine. So we're going to do 5.6 times 10 to the negative second moles per second. Right? So again, the biggest thing here, right? I'm not even worried about what the number is here. You could make this 5 times 10 to the 10. I'm worried about this. 2y over 1x. Because you're using the coefficients to compare the rate of appearance and rate of disappearance. So you take what you're given and you multiply by your coefficients. This is all you need, 2y over 1x. If you wanted to solve for q, instead, if it wanted rate of appearance of q, you could do 3q over 1x. That would give you q. So example 4. Now we're going to find a few different things. So example 4 gives us this balanced equation. So example 4 is right in the middle of page 4. Consider the combustion. If hydrogen is burning at the rate of 0.85 moles per second, what is the rate of consumption of oxygen? And what is the rate of formation of water vapor? So again, H2 is 0.85 moles per second. And so what we can do is just look at our balanced equation. So we need oxygen and water. So I'm going to look at H2 compared to O2. So for every 2 H2, we need 1 O2 that's consumed. So 0.85 divided by 2, 0.425 moles per second. Again, rates are positive, but what we can say here is we can say consumed. So oxygen is consumed, right? It's also burning at the rate of 0.425 moles per second. So notice oxygen's coefficient is half that of hydrogen, and its rate is half that of hydrogen. Then the rate of formation of water vapor. So again, start with what we know. 0.85 moles per second of H2. For every 2 H2, we form 2 H2O. So 2 over 2 is the same as 1 over 1. So based on the coefficients, if they have the same coefficients, they're going to have the same rate of formation or rate of appearance or disappearance. So water is forming at a rate of 0.85 moles per second. So depending on how you want to word it, right, we could say that oxygen is being consumed at 0.425 moles per second. Water is being formed or appearing at a rate of 0.850 moles per second. Now, rates are given as positive values. If you see this negative, that just tells you that it's being consumed. All right, so that just means that it's being used up. But we always report rates. So like if you're doing mastering will want you to report the rates as positive values. So that's looking at example 4. Reactions have rate of appearance. So, okay, reaction. So the products appear, the reactants disappear. So think about like in this balance. So for example, in example 4, or example 3, in either of them, in this balanced equation, H2 plus O2 yields H2O. Water, so water is being formed. It's appearing. Hydrogen and oxygen are being used up. They're disappearing. So reactants will always disappear. Products will always appear. So that's why if you actually notice, like if these are disappearing, we're looking at, what's happening overall. These are disappearing. So these are negative. These are appearing. These are positive. So reactants always disappear. Products always appear. Emily, would the overall rate be 0.425 because O has the lowest coefficient? Yes, it would. Yes. So the overall rate of reaction would be the same as oxygen because, yes, it has the coefficient of 1. Also, if we would think about it, instead of H2 here, if instead of going from H2 to O2, we were going to the overall reaction, for every 2 H2s, we have the reaction run 1 time. So the overall rate of reaction would also be 0.425. Yes. Yep. Will we do these problems with temp and other factors? Temperature, not as much. We will look at other factors. We'll actually look at how to determine what's called a rate law. We're actually doing that tomorrow using experimental data. So rate of appearance and rate of disappearance, you can only use once you know the rate. We're going to look at what happens if we don't even know the rate, how we can figure it out. Any other questions before we look at example 5? You guys are going to have lots of time as well. So we're going to go through the next 2 examples, and then you'll kind of have a break. You'll be able to go through and work on things on your own. So for example 5, this is more of a lab type example because this is the reaction of 2NO plus Cl2 yields 2NoCl is carried out in a closed container. So this is going to kind of tie gases back in too. If the partial pressure of NO is decreasing at the rate of 23 torr per minute. So I'm going to pause really quick. We can also look at rates of gases. So a lot of times what we're looking at is either rates of solutions or rates of gases. And if we're looking at rates of gases, it's going to be given in pressure over time. So know that when we see pressure over time, we don't have to convert anything, but that just means we're dealing with gases. So if the partial pressure of NO is decreasing at the rate of 23 torr per minute, what is the rate of change of the total pressure in the container? And then I kind of gave a hint here. I said the change in total pressure is the sum of the changes of each partial pressure. So we're going to look at example 5 up here on the whiteboard. So if you don't have the whiteboard pinned to the screen, I would pin this whiteboard to the screen just so that you can see it. So for this example, this is kind of 2 things in one. First, we need to figure out how are the partial pressures changing? What is the rate of change of each of the partial pressures, which is exactly what we've been doing. Then we have to figure out the total pressure. So here's where those positives and negatives would be useful. Because again, we will communicate rates as positive numbers. But if, like in the case of this, it wants to actually know how an overall container would be changing, we have to take those positives and negatives into account. So it tells us that the pressure of NO is decreasing at 23 torr per minute, right? NO is a reactant. Reactants disappear. Over time, reactants will disappear. they'll be used up. So NO is decreasing at 23 torr per minute. So what I want to do first is I want to figure out, what does that mean about the pressure of Cl2? And what does that mean about the pressure of NaCl? So again, we're going to do just like what we've been doing. For the pressure of Cl2, I'm going to start with what I know. I know NO. I know NO. So I'm not going to worry about the negative. I'm just going to worry about the value itself. So NO is changing at 23 torr per minute. I'm going to look at the balanced equation. For every 2 NOs, there's 1 Cl2. So right now I'm figuring out the pressure of Cl2. How is the pressure of Cl2 changing? So 23 divided by 2 is 11.5. So the pressure of Cl2, now it's a reactant. It's being used up. So the pressure of Cl2 is decreasing by 11.5 torr per minute. Okay, so here's the pressure of NO. Here's the pressure of Cl2. Pressure of NaCl. Now you can set it up like we have been. Or take a look at this. For every 2 NOs, you have 2 NaCls. It's essentially a 1-to-1 ratio. So whatever the rate of NO is also the rate of NaCl. However, NaCl is appearing. So NaCl is going to be positive 23 torr per minute. Again, you could set it up like this and start with NO, but it'd be 2 NO and 2 NaCl. So here's our partial pressures, NaCl, Cl2, NO. The question says, if I read the question again, what is the rate of change of the total pressure in the container? Well, we have the 3 partial pressures. We have the 3 partial pressures. Think back to when we did gases. You have the 3 partial pressures. How can you find the total pressure? So P total, I can just add them all up. But this is why the positive and the negative was important. Because if I'm adding them up, I still need to be taking into account the ones that are decreasing and the ones that are increasing. So I'm going to add them up. I'm going to do the pressure of NO plus the partial pressure of Cl2 plus the partial pressure of NaCl. And I'm just going to plug in the numbers that we solved for or that we were given. So partial pressure of NO, negative 23 torr per minute. Right? It's decreasing because it's a reactant. Partial pressure of Cl2, negative 11.5 torr per minute. Again, decreasing because it's a reactant. NaCl, positive 23. Increasing because it's a product, so it's appearing. Negative 23 plus negative 11.5 plus 23. So I just don't have a calculator. So negative 23 plus 23 is 0, which leaves me with negative 11.5 torr per minute. So the total pressure in the container is decreasing by 11.5 torr per minute. So all we did in this, and again, this is a very unique, I would consider this more like a challenge type of problem with what we've been looking at, where we had to find the rates of each gas, right? The rate of each pressure of the gas, add them all up to find how the total pressure is changing. We put that negative. The reason that we put that negative, even though rates are always expressed as positive numbers, is because this is specifically telling us that the total pressure is decreasing by 11.5 torr per minute. So if instead you just wrote 11.5 torr per minute, or you wrote decreasing by 11.5 torr per minute, you'd be okay. but that negative tells us that it's actually decreasing. Okay, so again, examples 4 and 5 kind of had the most amount of work. But again, all we're doing with rate of appearance and rate of disappearance is looking at the coefficients, right? And just multiplying by a fraction with the coefficients. So before we get to the last example, any questions on 4, 5, or 6? Again, if you have any, type them in the chat. All right, people very well might have the same questions as you. And I have the answers on this slide as well. So again, exactly what we wrote on the whiteboard. You don't necessarily see the math. I just wrote is half of, but you can see here. So you have two ways of representing this. Negative 11.5 torr per minute, or you could say pressure is decreasing at a rate of 11.5 torr per minute. Okay, so the last example, and then you're going to have some time, a lot of time on your own actually. So example 6, the graph below displays the change in concentration for each species in the following reaction. 2A yields 2B plus C. Label each curve on the graph as A, B, or C. So AP always likes tying things into graphs. So for this, all we're doing is labeling. Now, of course, you know that I'm going to give more information on this graph, but here's what we need to think about when we're looking at this graph. We have 2A yields 2B plus C. So we have one reactant, and we have two products. So the first thing I want to look at is I want to look at these lines. So I notice I have one line that's decreasing over time and two lines that are increasing over time because we have concentration versus time. So the one that's decreasing, right? Remember that reactants, your amount of reactant decreases over time. So this line that's decreasing, this should be A because it's decreasing over time. So we know that we at least have A labeled. Then we have these two lines that are increasing. So those are our products. But notice that they're increasing at different rates. Well, that's where we're going to look at these coefficients. So B has a coefficient that's twice as much as C, which means B is going to increase at twice the rate of C. So if we take a look at this graph, A is this one that decreases, B is the one that is increasing at a higher rate, C is the one that's increasing at a lower rate. And so over here off to the side, right, A is a reactant, so its concentration is decreasing over time. B has the same coefficient as A. So the rate that A is decreasing is what the rate of increase of B is. So the slopes of the curves should be similar between A and B because their rates are similar. And then it says 2 moles of B are formed for every 1 mole of C. So B is going to be twice as fast, or C is going to be half the rate of B. So it's going to be kind of half the slope. So this again is just looking at labeling your reactants and your products on a graph, but it's also thinking about the rates. So A and B have the same rate because they have the same coefficient. C has a different coefficient, so it's going to have a different rate. And because its coefficient is half that of the other ones, its rate will be half of the other ones. Okay, so any questions on the examples that we've looked at? And again, I have this recorded, so if you need to go back and you need to refer to them, you can. If you're looking back over things and have questions, I'm more than happy to answer questions. But the biggest thing to remember is that you don't have to do that complicated formula that's in the textbook. I can't believe that I just learned about this way because this is so much easier. You're just using the stoichiometry when you're looking at rate of appearance and rate of disappearance. So for the rest of class, you have about a half an hour until the end of second period. I'm not going to require you to stay in the meet. So for the rest of class, you can work on mastering. So up through number 7. So remember, just pay attention to those that are extra credit versus actual points versus practice. And I believe that's out of the first 7. Number 2 is practice. So you'll notice it says 0 points, 1 and 6 are extra credit. The rest are worth points. So really you have, what, 4 points, 2 extra credit. And then you can watch video 5.2. So that is up in Google Classroom. So I want you to have 5.2 watched for tomorrow. Tomorrow is really when we're going to dive into the problem solving with rate laws and talking about rate constants and things like that. So if you would rather just use this time to watch 5.2, you can. So whatever works best for you is what I, will have you guys do. Again, you do not have to remain in the Google Meet. You can, let me stop recording this. You can, if you want to stay in, you can. If you